In this video lecture, we're going to discuss how we can find the volumes using the integration. Before we do this, let's quickly discuss how we actually use the integration to find the areas. The essential idea of using the integration to find areas was that we are going to use the fact that the area of a rectangle is going to be the multiplication of their sides. So just using this idea, if I would like to find the area under some function and the area between a and b, for example, we're given some function, non-zero function, for example, like this. And if I would like to find the area under this function, we just need to split the area into the many small rectangles, and by just summing those rectangles, we can find the area. For example, if we just split this into the two rectangles, so this is going to be our x0 point, this is going to be our x1, xt, and this is going to be our x3 point. Then it's going to be, so the area under this function is going to be split into the three small rectangles, and we can find those areas by just multiplying the height to the width, right? So it's going to be my first rectangle. Then this is going to be my second rectangle. Then this is going to be my third rectangle. So the area of the first rectangle is going to be f of x1, which is the height of this rectangle, right? Which gives me this height, multiplied to the delta x. The area of the second one is going to be f of xt multiplied to the delta x. And the area of the third one is going to be f of x3 multiplied to the delta x. So by summing the three areas, we can find the area under this function. So in general, we wrote down that the area is going to be the summation of f of xi. I put star because depending on which sample point we're going to choose, so this x is going to be different. Multiply to the delta x. This is going to give us roughly the area, and we know that we can get more precise answer if we increase the number of the rectangles. So if basically instead of taking 3 rectangles, we get 6 rectangles, our result is going to be better. If we get like 600 rectangles, it's going to be even better. So its limit when n goes to the infinity is going to give us the exact area, and we usually write this as a definition of the integration. So we basically integrate our function with respect to the x from a to the b. So this is the basic idea how we're going to find, so this is going to be the fundamental idea how we're going to find the volumes. So first of all, let me remind you that the volume is actually, so the volume, for example, of the box is very much similar to the volume of the rectangle. So if you know the area of the base of this box, so basically if you know that its sides, its area is going to be equal to the a multiplied to the b, we additionally have to multiply this to its height in order to find the volume. So the volume is always the area of the base multiplied to the height, no matter what is the base. If the base is, for example, is a square, then it's going to be a multiplied to the a. If the base is the circle, then the area is going to be 2 pi r, and so on. For example, if we've got the circular cylinder, means that its base is going to be a circle. Then the volume of the circular cylinder, it's going to be the area of the base multiplied to the height. So in order to find the area of the base, we need to know the radius, its radius, right? So this is going to be equal to 2 pi r multiplied to the height, to the h. So now what if our, so we would like to find the volume which is not standard one. So basically it's not the box or it's not the cylinder. Then how to find the volumes in that case? So let's say we've got So for example, I've got an object like this one. So this is going to be our x-axis. So we just need to find its volume where the x is going to change between A and B. And the essential idea is to make a slice. So we are going to make a lot of slices, and by just like summing the volumes of those slices, we can find the overall volume. So let me explain you what does it mean. So I'm going to choose some point x star, let's say. It's going to be our sample point. At this point, I'm going to create a slice. So I'm just going to cut this object at some point here. Then I'm just going to cut this in a little more distance here as well. So just with some width or with some height, let's say. It's going to be this kind of slice. And the volume of the slice is going to be so analogously to the volume of this circular cylinder. So we approximately take the base of the circular cylinder here as the circle. So it's going to be the area of the base multiplied to, so at some point x, multiplied to the delta x. So this is going to give us this volume. So we can find this volume, for example, here. So let's say x1 star, let's say. So the idea is again the same. So we are going to create the slice. So we're going to cut this a little bit here, create one more slice, and the volume of this slice is going to be equal to the area at this point, x1 multiplied to the delta x. So we're going to find the overall volume by just making a lot of slices, and by just summing the areas of those cylinders, we can find the overall volume. So the volume is going to be equal to the summation of the area of the slice at some point xi multiplied to the delta x. So where I goes from 1 to the n. So basically we're going to make a lot of slices, right? So actually this formula very much similar to the formula of the area, right? Except previously we used to have the function which gives us just the height, and now we've got a function which gives us the area. So this is going to give us roughly the volume, and if we would like to get more precise results, we just need to increase the number of those slices. So basically, if the number of the slices in goes to the infinity, then this becomes exactly the volume. And this is basically the definition of the integration to find the volumes. So it appears if I would like to find the volume of an object, we just need to integrate the function of the area with respect to the x, where x is going to change from a to the b. So this is going to be the definition of the volume, and this is how we can find the volumes using the integration. The most important part in this formula is how to define this function ax. So this is the most difficult part, I would say. So let's do an example in order to understand how to use this formula actually. So example. So let's say we would like to find the volume of a sphere. So let's say, let's put the coordinates here as well. Okay, so I've got a sphere with a radius r. So basically, let's find the volume of a sphere with the radius r. So it's going to be a 3D object, actually, and we would like to find its volume. So again, the essential idea would be to just create a lot of slices. For example, I choose one point here. I'm going to create a slice. I will just cut this sphere at this point. So if we cut this, it's going to be this kind of slice, right? And being able to find the area of the slice is one of the most important things which we need to do in order to find the volume. So we are going to create a lot of slices. So we can find a slice here, or we can find a slice here. And by just adding up the volumes of those slices, we can find the volume. So from where to where we have to make the slices? Basically from this point until this point. Since the radius of the sphere is given as the r, so which is some number, for example, 2 or 3 or 4. So this point is going to be a minus r on the x-axis, and this point is going to be plus r on the x-axis. So we have to create the slices from minus r to the r. And the volume, so let me write this with a different color. So the volume of a sphere is going to be the integration of the area function, which is going to depend on the x, with respect to the x, from minus r to the r. So, this function, finding this function, is one of the most important parts of our work. So basically, so do you see here? So depending on which point on the x-axis we're choosing, the area of the slice is going to be different, right? So obviously it depends on x. So we need to figure out the function which is going to give us the area of the slice depending on where we are. So for example, if I choose this point here, what is going to be the area of the slice? So this area, so the slice actually is the circle. So we don't really see this from here, but you can imagine that if you got a ball and if you make a slice, you will get a circle there, right? So the area of the circle is going to be, so the radius in the square multiplied to the pi. So the radius of the circle actually is equal to the height of this function, right? And what is that function? Is just the function of a circle. So basically, if you are given a sphere, then this function is going to be the equation of a circle. So if you remember, so the equation of a circle is equal to the x squared plus y squared is equal to the r squared in this case, right? So we need to find a y from here. So if we find a y, it's going to be r squared minus x squared from the square root, and we have to take the plus and minus. So basically, this function, the upper half of a circle, is going to be with the plus square root of r squared minus x squared. The lower part is going to be with the minus. So obviously, so here, if this x is equal to some number, if I just substitute this to here, so this function here, it's going to be y is equal to the plus r squared minus x squared. What does it mean? It means that if I would like to find the height of the point here, I just need to substitute this x to this function. It gives me the height. So basically, the area at any point x is going to be the radius of a circle of that slice in the square multiplied to the pi. And that radius actually is equal to the height of the point, which we can find using this function, right? It's going to be a square root of r squared minus x squared in the square multiplied to the pi. So if we just open the brackets and simplify the things, we will get the r squared minus x squared multiplied to the pi. Well, this is going to be the area function, and this is the most important part in our job. So basically, so whenever you make a slice, so if you know your position, if you know where did you make the slice, for example, if you made a slice at this point 0, x is equal to the 0, if you substitute the 0 to here, it's going to be r squared multiplied to the pi. Indeed, the area of this slice is equal to the radius of a sphere, which is r, multiplied in the square multiplied to the pi, right? So depending on which location we're making the slice, we can find the area. So let's find the volume now. So the volume is going to be the area, which is r squared minus x squared multiplied to the pi. Its integration with respect to the x from minus r to the r. So let's integrate this. It's going to be r squared multiplied to the x minus x cubed over 3 all of the things is multiplied as a pi, and we have to evaluate this for the r and for the minus r. So let's evaluate this for the r first of all. So what does it mean? It means that I just need to substitute all the appearances of x with the r first of all. It's going to be pi multiplied to the r squared multiplied to the r minus r cubed over 3. So now we have to substitute minus r instead of x. It's going to be minus. So the pi multiplied to the r squared multiplied to the minus r minus r cubed over 3. Well, we just need to open all the brackets and work with the numbers. It's going to be so r cubed minus r cubed over 3. It's going to be 2r cubed over 3, right? So this is r cubed. This is r cubed over 3. So if I just subtract them, it's going to be 2r cubed over 3. It's going to be pi r cubed over 3 multiplied to the 2. Minus, so let me just introduce this minus inside. It's going to be, if I just multiply this term to the minus, it's going to be r cubed. And if I just multiply this minus to the second term, it's going to be a minus r cubed over 3, right? Because I've got 3 minuses. So there is one minus here, the second minus here, and the third minus here. So overall, it's going to be minus r cubed over 3. So if I just subtract this, it's going to be again r cubed over 3 multiplied to the 2. So it's going to be 2 pi multiplied to the r cubed over 3. So these two terms are the same. So if we just sum them, it's going to be just multiplication of this of one of this term to the 2. It's going to be 4 pi r cubed over 3. Well, that's the formula of the volume for the sphere, which we know from the school, and we can obtain this using the integration. So in our next video lectures, we're going to learn how to find the volumes of any arbitrary object using the integration.